everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I am dealing with the course Computational Aerodynamics. And in today's topic, we will see the tutorial question bank on the module 3, which is basic discretization methods, which are available in computational aerodynamics. So basically, we will see what is discretization. So how do you discretize the partial differential equations, which we have learned from the module 1. And in the module 2 we have seen basically the classification of those partial differential equation, and we have seen the boundary condition. So in this module basically we will see how to change those partial differential equation in discretized form. So that terminology we will be seeing in this tutorial question bank. Okay, so here we can see that we need to derive the discretization method from Taylor series of expansion for forward, backward, and central difference methods using finite difference methods. So basically, in computational aerodynamics, there are two methods. So we have FDM, which is called finite difference method, and we have FVM, which is called finite volume method. So when you take a mesh, so here for the finite difference method, so we are solving the governing equations at these grid points. Okay, so when we solve these governing equations at the grid points, so we call these as a finite difference method. So finite volume method in the sense, so we will have to estimate the center of the cell. So how many cells we have? Cell 1, 2, 3, 4, 5, 6. So we have 6 cells. Okay. So for each cell, so you need to find out what is the centroid of the cell. So let's say, so we have 1, 2, 3, 4, 5, 6. 6 centroids are available. So whatever the average properties that you have at different phases, so will be estimated at the center of the cell. So that is we have finite volume method, so which we will discuss in the module 5 actually. Okay, so now basically the meaning of discretization is, so to convert this partial differential equation, let's say du by dx into linear form actually. Okay, so when you change this partial derivative in linear form in terms of index notation, that methodology is called the discretization. So basically we do using Taylor series of expansion. So we'll just recall, so basically what is the formulation of Taylor series of expansion. Okay, so we will take function f of x plus delta x, so which is equal to f of x plus dou f of x by dou x into delta x divided by 1 factorial plus dou square f by dou x square into delta x square divided by 2 factorial plus dou cube f of x by dou x cube into delta x cube divided by 3 factorial plus so on. Okay, so this is what we have for Taylor series of expansion. Now, so in the index notation, so we are converting index notation where x is nothing but index I, so y is nothing but index j, so z is nothing but index k. Okay, so this is what we have. So now delta x is nothing but the distance between two grid points. So here you can see, so this grid point and this grid point, so whatever the horizontal distance, this is called delta x, and this is called delta y. So this is called delta x. So basically x1, delta x2. Okay, so delta y, delta. So here you have delta y3, delta y2, so delta y1, something like that. You can see that. So if delta x1 is equal to delta x2, so we call it as uniform grid or mesh. So along x. So if delta x1 is equal to delta x2 is equal to delta y1 is equal to delta y2 is equal to delta y3, then we call it as this is along x-axis. So globally it is uniform mesh or grid. Okay, so globally we call it as. Now, so what we are doing actually, so we are the delta x thing, so is nothing but the spacing. So the delta x can vary from let's say 0.00 let's say 0.1, or it can be as small as possible and can be as large as possible, but based on the thickness of the boundary layer, or let's say the resolution you want, you will change the delta x. So it purely depends. There is nothing rule that you have to follow this delta x and delta x, but the pure experimental and pure numerical simulations. So whatever the flow field it need to capture. So based on those characteristics, so we need to choose what is the value of delta x. Okay. So for example, let us take the delta x value here. It will take it as 1. Okay. Let us take x as I. So how do we change the index notation? Okay. So you can keep it as f of I plus 1, you can see. So which has come for f of I. Okay. So dou f by dou x into delta x. What is? There is 1 divided by 1 factor. So on it will become in this way. Okay. So this is how we actually do these things. Now let us concentrate what is basically forward difference. So how do we get? So we have, this is LHS term. So RHS first term, second term, third term, fourth term, so on you have. Now what we do is like, so we will send this RHS first term to the left hand side. Okay. And we will calculate what is the value of dou f by dou x. Why? So we are finding, so what is the value of first order derivative. So in continuity equation, we have dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So this is continuity equation. So for this continuity equation, we have this first order derivative term. So for first order derivative term, so we will actually find in terms of this linear expression. That's why, so we are replacing these terms with respect to dou f by dou x. So we'll see by rearranging it. So what we'll get, we'll see it again, we'll write it again. Of x plus delta x is equal to f of x plus dou by dou x of f of x into by 1 factorial by 2x squared 2 factorial plus 3 factorial plus so on. So we have these things. Now what do? We rearrange. So f of x plus delta x minus f of x is equal to dou f by dou x into delta x plus, so the remaining terms, so these terms, they are called truncation error terms, so, or you can say higher order terms. Okay, higher order terms. Okay, so we'll send in this way. So we'll send the higher order terms in this way. So finally what happens? So dou f by dou x is equal to f of x plus delta x minus f of x divided by delta x. So here it will be minus So what are the terms? So here are the terms we have: dou square f by dou x square into delta x square divided by 2 factorial plus so on. So here divided by delta x. So the leading error term is order of delta x. So what we will do is like, so dou f by dou x is equal to f of x plus delta x minus f of x divided by delta x. Let's say you take plus order of accuracy of delta x. Why? Because what we are doing, so we are neglecting so the first term, which is power of delta x. So that's why we call it as order of delta x. Okay. Now, so this first order derivative term, so dou f by dou x is equal to f of x plus delta x minus f of x by delta x plus order of accuracy of delta x. So this is the formulation for forward difference. Okay. So let us replace in terms of index notation. Okay. So let us take f is equal to some iu. Okay. So dou u by dou x at I, index I, is equal to, so what happens? So u of I plus 1. So let us take delta x as 1 and let us take x as I. Okay, minus u of I divided by, so here you can take delta x. So in this notation. Okay. So now what happens actually? So we can write in this way also. So u of I plus 1 minus u of I divided by delta x. Okay. So you can take this as 1. So if you want to write in index notation, so u of I plus 1 comma u of minus u of I divided by delta x. So this is for forward difference. Okay. So this is for forward difference. So how do we get backward difference actually? So backward difference. Again we'll go back to Taylor series of expansion. What? F of, instead of plus we will do x minus delta x. Okay, which is equal to f of x minus, okay, dou f by dou x into delta x divided by 1 factorial plus dou square f of x by dou x square into delta x square divided by 2 factorial plus so on. Yeah, so on. Okay. So this is what we have. Now what we will do, we will rearrange. So what we get is, so dou f by dou x into delta x is equal to f of x minus f of x minus delta x. This is the first term. Next you have minus dou square f by dou x square into delta x square divided by 2 factorial plus so on we have. Okay. So we'll send this way. So when you send this delta x to the right hand side, so this becomes delta x here divided by delta x. So even in the backward difference also you have the first order term which is of order of delta x. So what we do? So dou f by dou x is equal to f of x minus f of x minus delta x divided by delta x plus order of accuracy of delta x. So let us write in index notation. So what do we get? So f of I minus f of I minus 1 divided by delta x, so which is of order of accuracy of delta x. So this is what we have index notation, so which is for backward difference. Okay. So let's see for the central difference. So basically what is central difference? We see. For that, we need to do the changes, the manipulation or the changes for both forward difference, backward difference formulations obtained from the Taylor series. So what we will do is like, so we'll take f of x plus delta x. We'll take f of x minus delta x. Okay, so which is equal to f of x plus dou f by dou x into delta x divided by 1 factorial plus dou square f by dou x square into delta x square divided by 2 factorial plus dou cube f by dou x cube into delta x cube divided by 3 factorial plus so on. Here also we have, so f of x minus dou f by dou x delta x divided by 1 factorial, so plus dou square f by dou x square by 2 factorial, so minus dou cube f by dou x cube delta x cube divided by 3 factorial plus so on. So what we do is like, so let's say we have equation 1, so we have equation 2. So we will subtract equation 1 from 2. Okay. So what happens? This term, this will get cancelled. So these two terms will get added up. So this term will get cancelled. So this term will add up. So when you subtract equation 1 with 2, so the odd derivative terms will remain and even derivative terms will get cancelled out. So what happens? So f of x plus delta x minus f of x minus delta x is equal to 2 times of dou f by dou x into delta x plus 2 times of dou cube f by dou x cube into delta x cube divided by 3 factorial plus so on. Now when we rearrange, so what happens actually? So dou f by dou x is equal to f of x plus delta x minus f of x minus delta x divided by 2 delta x plus, minus, so dou cube f by dou x cube into order of delta x square divided by 3 factorial into 2 plus so on. So here what is order of accuracy? So the order of accuracy of this scheme is delta x square. So when you see the forward difference, when you see the backward difference, so the order of accuracy was delta x. So for central difference, it is delta x square. So what is this? Dou f by dou x is equal to, so f of I plus 1 minus f of I minus 1 divided by 2 delta x. So which is of order of accuracy delta x square. So this is for central difference scheme. Okay, so let's compare actually. Okay, so let's compare what happens. So we have, so this is as central difference CD. Okay, so this one as backward difference BD, and so this one as forward difference FD. Okay, so when we write here, so here we'll compare. So f of I plus 1 minus f of I minus 1 divided by delta 2 delta x plus order of accuracy of delta x square. So this is for central difference. Similarly, so f of I plus 1 minus f of I divided by delta x plus order of accuracy of delta x, so which is forward difference. So you see 1, you see 2, you see 3, let's say. So from 1, 2, 3, we can see that, so the order of accuracy for forward difference is delta x, for backward difference also it is delta x, but for central difference it is of delta x square. So it is having high order of accuracy. Okay, so with this we have seen the discretization method from Taylor series of expansion for forward difference. backward difference, and central difference using finite difference method. So in the next module, so we will see. So basically, what type of higher order accurate numerical schemes that we obtained using Taylor series of expansion. So let's say we have a dou f by dou x. Next, how do we get dou square f by dou x square? We need to see. So how do we discretize those equations? Basically, these things which we calculate or which we obtain, so we'll substitute these terms or discretize the equations in continuity equation, in momentum equation, and in energy equation to linearize those partial differential equations. So basically, the partial differential equations are very difficult to solve. So what we need to do is we need to convert the partial differential equation PDE to ODE and linearize them and get the solution. But here the discretization method is giving a straightforward terminology or methodology where you can change that to directly in a linear form. Okay, so in the next session we will see how do we do the discretization for the second derivative, and we will substitute the full form second derivative and first derivative equations in the continuity, momentum, and energy equations, and we will see full-fledged governing equation in discretized form. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.